You know that feeling, right? That sudden, jarring thump when you hit a pothole you didn't see coming? But what if our cars could actually hear the road breaking down and tell us exactly where to fix it long before it ever gets that bad? Well, a fascinating new research paper is digging into exactly that. I mean, just think about the sheer scale of the problem for a second. How on earth do you find every single little crack on every single road in an entire city, let alone an entire country? It seems almost impossible to keep up before those little cracks turn into massive, expensive problems. So the way we do it now is pretty old school. Technicians literally go out and do manual surveys using a system called the Pavement Condition Index, or PCI. Basically, roads get a score from 100, which is good, all the way down to 0, which is failed. Now, this system is super important, but let's be honest, it's also incredibly slow, it's expensive, and it can even be dangerous for the inspectors out there on busy roads. So all of that brings us to a much, much smarter idea. But like a lot of smart ideas, this one comes with its own sneaky little hurdle. We're talking about listening for cracks. Okay, so what if our cars could just do all the work for us? What if they could actually feel the road as they drive? Just about every modern car, and definitely your smartphone, has sensors called accelerometers. And the vibration data they pick up could give us this continuous, real-time map of our infrastructure's health. And the best part? It's super cheap. It's a brilliant idea. But here's that hurdle I mentioned. The raw data is basically just a bunch of noise. If you look at the vibration signal from a car's sensor, it just looks like a chaotic, squiggly line. You can't just glance at it and say, yep, there's a crack. It's just this complex jumble of information that's pretty much impossible to interpret directly. And this, my friends, is where the real magic starts to happen. To make any sense of that noise, researchers use a really cool technique called time-frequency representation. The whole idea is to turn those invisible, one-dimensional, squiggly lines into visible, two-dimensional pictures. Actual images that a computer can look at and analyze. Which leads us to the first major challenge, creating a clear picture. And I'm not talking about just any picture. We're talking about turning all that random noise into the absolute perfect snapshot of what's happening on the road. The special tool they use for this is a type of highly flexible mathematical lens called Generalized Morse Wavelets, or GMWs. Honestly, the best way to think about them is like a super advanced camera lens. You can tweak and adjust it with incredible precision to transform that messy vibration signal into a sharp, clear image, which, by the way, has a technical name, a scaleogram. Okay, but that brings up the million-dollar question. How do you find the perfect focus? A lot of earlier studies basically just guessed the settings for this mathematical lens. It was a lot of trial and error. But the researchers on this paper, they wanted a real scientific way to find the absolute best setting. And their solution is this really clever process called the Armsy method. So here's how it works. They pick a lens setting, they create a picture with it, and then, and this is the brilliant part, they try to rebuild the original vibration signal using only that picture. They measure how close they got, and then they do it again and again, thousands of times. The big idea is that the best, sharpest, most accurate picture is the one that lets you reconstruct that original signal with the least amount of error. And after all of that meticulous testing, they found it. They landed on a very specific optimal beta setting of 1.3333. Now, this isn't just a random number they pulled out of a hat. This is the scientifically proven value for getting the sharpest possible picture of this specific kind of road vibration data. And check out the payoff. It's incredible. On the left, you see the picture of a nice, smooth, uncracked road. The energy's kind of spread out, right? But look at the image on the right. For a road with a crack, bam, a bright, concentrated blob of energy just pops out. With that perfect focus, that crack becomes totally visually unmistakable. Okay, so we've got these crystal clear pictures of road cracks. Awesome. Now, how do we get a computer to automatically see and recognize them for us? Well, it turns out the researchers found a really ingenious shortcut. So trying to build an artificial intelligence from scratch is, as the paper itself says, viewed as an art. It is incredibly time-consuming, and it takes just mountains and mountains of data to teach a computer what a crack even looks like in one of these pictures. So instead of building an AI expert from the ground up, they use this brilliant shortcut called transfer learning. Here's the best way to think about it. Training from scratch, that's like trying to raise a world-class art critic from birth. It would take a lifetime. Transfer learning, on the other hand, is like hiring a world-class art critic who already understands color, composition, and history, and just giving them a quick tutorial on a new style of art. It is way, way faster and more efficient. And these are the world-class art critics they hired for the job. 3 incredibly powerful pre-trained AI models you may have heard of: GoogleNet, SqueezeNet, and ResNet 18. These AIs have already been trained on millions of other images, so they're already experts at spotting patterns. Which, of course, leads us to the big question. It's time to put this to the test. How well did these expert AI critics actually do when we asked them to spot road cracks? The results? They were fantastic. Using a metric called the F1 score, which is a really good way to measure overall accuracy, both SqueezeNet and ResNet 18 scored right around 85%. Now, ResNet 18 was a tiny fraction better, but honestly, both were incredibly effective at spotting the cracks in those vibration images. But here's where it gets really interesting for anyone thinking about using this in the real world: the training time. ResNet 18 took almost 6 minutes to get up to speed, but SqueezeNet? It needed less than 3. It achieved almost the exact same top-tier performance in less than half the time. That kind of efficiency is a total game changer. So when you step back and look at the whole project, the real breakthrough isn't just one successful AI model. It's the entire framework. What they've created is a scientific, repeatable process to turn noisy, messy data into clean images and then efficiently teach an AI to read them. This isn't just a one-off trick. This is a blueprint. And this is exactly why it all matters so much. The paper itself notes that this whole approach is getting a lot of attention because of its cost-effectiveness and potential real-time execution. This is pointing to a future where basically every car on the road could be a tiny, mobile road inspector, constantly and automatically mapping problems as they happen. Which leaves us with this one last, really fascinating question to think about. This whole thing is about so much more than just filling potholes. What if our cars could do more than just tell us where the roads are breaking? What if they could actually help us build the smart, self-monitoring, self-maintaining roads of the future?